Yeah, hi. I welcome you all to this seminar, and thank you for joining. And as this is the 17th of this series, I have the freedom to refer you to many of the previous talks for many of the things that I'll be talking. But my topic today is about understanding the LIGO black holes, by which I mean LIGO has seen many of the black holes so far, and I will be explaining what we have understood about them and what they have helped us understood about the universe itself. In some way. So the broad outline would be to just start with the basic idea of what are black holes for those who are, and just to make sure we are on the same page, and what are the gravitational waves from binary black holes look like. That's what actually LIGO sees. And then talk about what black holes LIGO has seen and what kind of properties have we inferred about them. Then I will be ending with what we are looking forward to in terms of their when what more could we be doing in the coming years and decades and so on. Okay, so with that, I think that's black holes are extremely fascinating objects. At the same time, they're simple in the sense I will talk in a moment. Then the important thing, so what is shown on the left-hand side is the artistic depiction of a black hole. And so the important thing about black hole is that the gravitational field of black hole is so strong that almost nothing can come out of it. Nothing can come out of it. Things can only go in, but nothing can come out. And in a way, a black hole has got a singularity at the center, and singularity is a point where no known physics can be used to explain the physics there. And then it is horizon, which covers the singularity, and that's all what a black hole is. Now, all that we can talk about a black hole is outside, as I said, and hence for us, a black hole is just a singularity plus a horizon. Horizon is a fiducial surface which will cover the singularity. So this is one of the predictions of Einstein's theory, but any theory of gravity can in principle have black hole solutions, though their properties will be or can be quite different from that of GR. So simplicity of a black hole is basically that it is completely characterized by mass and spin and charge also in principle, but astrophysical black holes, since in the astrophysical environments, charge is not a black hole can sustain for long. So immediately it will be charge neutral. And so you're looking into black hole, astrophysical black holes of GR, which are completely characterized by mass and spin. So mass is how heavy it weighs and spin is how rapidly it rotates. Right? And it is believed, believed that they are formed at the end stage of massive star. When the massive star exhausts fuel, it will implode, and the implosion will lead to the formation of black hole. And that's how we believe all these black holes that we are seeing are produced. Now, I strongly recommend you to, in case you haven't already, there's a lecture by Professor Shamak Rai Chowdhury, who has talked about various aspects of black holes in great detail. So since I am not covering many of them, I would strongly recommend you to go over that lecture when you get time, and if you are not already done so. Okay, so how do we observe black holes? So electromagnetically, a black hole can be observed through things which fall into that. So if there is a matter that is falling into a black hole, that's called accretion by a black hole. This could, it could get heated up, it could emit light in various bands, and this electromagnetic waves or light that we receive from the infalling matter onto a black hole is what we use to understand it. So depending upon the mass and so on, the accretion rate and the spectral features could be quite different. And very broadly, we classify black holes into three in terms of the masses. So the first class is called stellar mass. Stellar mass black holes will be a few to tens of solar masses black hole. So if you have a stellar mass black hole, maybe 10 times the mass of sun, that is the mass of the black hole. Then, so usually these are, and at least one place where we have found them astrophysically is in a binary system where you can have a black hole and a companion, and the black hole could be accreting from the companion. So the matter which falls in from the companion are seen in X-rays, and these are called X-ray binaries, and we know many of such binaries exist in our galaxy. And so this is an example of a stellar mass black hole. Now, second class of black hole, which are less understood, are called the intermediate mass black hole. So these are, it could weigh roughly between hundreds to thousands or 10,000s of solar masses, depending upon the details. And especially this is a class of black holes which are yet to be understood even electromagnetically. We still have no clear or non-ambiguous cases for this. But we believe that they may be found naturally in the centers of star clusters. So when there are clusters of gravitationally bound stars, and at the center of them, we believe that it could be harboring intermediate mass black holes. So that's again something that we know, or partly from observations, partly from theory. And the next class of black holes are called supermassive black holes. So typical masses could be from millions to billions of solar masses. And these are very widely believed to be existing at the centers of galaxies. So like our galaxy, for example, we know that there's a black hole with over 1 million solar mass. And almost at the center of every galaxy now, it is widely acknowledged that they will all be having a supermassive black hole. The masses could vary depending upon the type of galaxy and various other things. So we have got three classes of black holes: stellar mass, intermediate mass, and supermassive. And mostly I will be talking about stellar mass black holes because that is what LIGO is sensitive to for some reason, which I will come to. So right now, all that we have to keep in mind is that the electromagnetic observations of black holes come from matter that falls into the black hole, and it emits as it goes in. Okay, so as you know, I'm sure that you have heard lectures on gravitational waves before. LIGO or Virgo or any that kind of ground-based gravitational wave observatories observe black holes via binary black hole mergers. So these are binary black holes, meaning two black holes which orbit around each other, and they merge eventually. I'll show you how they do that. These are the black holes that we have access to. So all the LIGO black holes are mostly black holes in binary systems, either containing two black holes or a neutron star and a black hole. But I'll be mostly restricting my attention to binary black holes throughout the talk. So we are now going to be focusing our attention to binary black holes as the case for the line. So then, of course, what is shown on the left-hand side is artistic depiction of a binary black hole merger at the center. And what is shown are the ripples of the space-time that this dynamics is sending out. And as you know, gravitational waves are ripples in the curvature of space-time. So they go out from the place where the binary black hole is merging. And this will reach us. And LIGO-like detectors are sensitive to these gravitational waves, which are produced by macroscopic motion of the black hole. And as they merge, so they become stronger and stronger. And as they merge, they make very strong gravitational signals. But these are produced by the motion of the black hole. So these are basically emitted by the black holes themselves. And that's what we see, as opposed to electromagnetic observations, which are what we see are the matter that is falling in and them emitting. So we are seeing actual emissions from black holes themselves. But there is no contradiction because we are not seeing the interior of black hole. We are seeing two black holes merging and what is happening outside. Just that the gravitational wave emission is coming solely from the binary black hole dynamics itself. And that is what is interesting for the rest of the talk. So just a quick recap about what gravitational waves are. So they are, as I said, they are ripples in the curvature of space-time. They are basically propagating gravitational fields, very similar to electromagnetic waves, which are in some sense propagating electromagnetic fields. They are produced by accelerating masses, similar to electromagnetic waves, which are produced due to accelerating charges. They are transverse, just like electromagnetic waves, because in the sense that the effect they can produce is transverse to the plane of propagation. So if that is going straight into this wall, the effect of the passing wave will be shown on the wall. That's what is meant by a transverse wave. And there are two states of polarizations, and that is very similar to electromagnetic waves, though the details of it is different. So that is number of polarizations are same for both. And the one big difference between electromagnetic waves and gravitational waves is that gravitational wave interacts very weakly with intervening matter, because gravity is one of the weakest of the fundamental forces, unlike electromagnetic waves. And hence, in that sense, when we observe something from far off, we are getting almost uncorrected information about the phenomenon or the source. And in that sense, it is an advantage. At the same time, since it interacts very weakly with matter, it also interacts very weakly with the detector, and hence is a big challenge to detect these waves, which I will not go into. But that's why you took 100 years after its predictions to detect them directly. So one important difference between them is that gravitational waves are quadrupolar, at least in GR, by which I mean, compared to electromagnetic waves, which are dipolar, we know a dipole oscillation can give you electromagnetic waves. But the gravitational waves require non-sphericity and time-varying non-sphericity. That's what the gravitational waves were required to be produced. So this is just showing typical picture, but I'll not use it more. Okay, now what I'm going to show you is a numerical simulation of a binary black hole merger, and the waveform, which is at you can see the graph, the wave, how the waveform evolves as a function of time. And this is obtained by, so this actually is simulation from the SSX collaboration. These are numerical relativists who try to solve Einstein's equation and evolve the binary and try to extract gravitational waveform from the system. And you will see that as the binary, so basically what you are looking to see are two black holes are orbiting around each other. They lose energy and angular momentum and so on. So as they lose energy, they come closer. As they come closer, gravity is stronger, so they emit stronger. So then it's like a runaway process, which will end only if you bring them close, and then it will make them merge. And that is the merger that we are seeing as binary black hole mergers. And the waveform that is shown. So as the simulation goes, you will see how as a function of time, you will see the waveform to be evolving, and you will be noticing the formation of a new black hole, and then how that black hole settles down to a stationary kind of geometry. So I'm going to play the animation now. So these are two black holes far away. They will come closer. You can see the emission is almost sinusoid, though there is a small frequency evolution which is not that evident. So now they have entered the late stage of the evolution, which is very fast. So things will be going fast, and the waveform will be evolving faster. And you can see a chirp-like signal. Okay, this is the formation of a new black hole, and then it sort of settles down. So that is what it is. So you have seen two black holes coming from far away. They come closer and closer, emit stronger. They have a pattern where the frequency and the amplitude is evolving as a function of time, increasing as a function of time. And then they eventually form a new black hole, which sort of settles down to a stationary geometry. And then the emission ends, and then we have zero amplitude, and there's no wave left. So now what I've shown you in this picture is the image of the waveform reconstructed from the first binary black hole that LIGO detected. It's called 150914, named in the 2015 September 14 is when it was detected. So that is what is shown. So you can see that the early stage of the inspiral, where things were almost monochromatic or sinusoid, is called inspiral. That is a time where this shrinking time scale is much can be ignored, and things are almost sinusoid. But as they come closer and closer, as you can see in this picture, the frequency increases in the sense that the two peaks come closer and closer, and the amplitude increases because they emit stronger, because they are in a strong field regime, they emit even stronger. So you can see that the inspiral and merger happens when very close to this peak. You don't know exactly what to call a merger, but this happens very close to this the peak. And then they form a new black hole. This black hole formed is deformed black hole, as you can see. And this black hole, newly formed black hole, also has got non-sphericities, which it will send out as a wave. And this last part is called a ring down, which is like a damped sinusoid, as you can see. It's a sinusoid with a damping, exponentially damped sinusoid. And that is called a ring down or a quasi-normal mode. So the inspiral part is, and the merger and ring down are the three phases of the evolution. And the interesting thing about this phenomenon is that you can model using Einstein's relativity. You can model both all the three phases of the evolution. either using analytical techniques, which is possible for inspiral and ring down, or using numerical relativity, which is required for modeling the strong field dynamics close to the merger. So basically, you can calculate, you can evolve and calculate the waveforms expected out of this kind of mergers and be ready with the waveforms that you are looking for. And so what is shown, I'll come back to that thing. And if you want to understand more about the waveform modeling, there's a lecture by Bala Iyer in the same series who talks in length about the history and the physics of the waveform modeling. I will not be going too much into the details of that in this talk. So it is also important to keep in mind that the bottom panel shows you the velocity as the systems come closer and closer, and close to the merger, when they are merging, the velocity is comparable to the speed of light. It's like 0.5 or 0.45 times the speed of light. So that would mean that you're really looking into relativistic collisions of black holes, and the field is extremely strong and extremely relativistic, and almost everything that you can think of is extreme. So that is why these are very amazing phenomena which can be tracked only via gravitational waves, and that's what makes LIGO to be an excellent detector. Okay, so that's about, so the thing to keep in mind is that the different stages of the binary evolution can be well modeled using Einstein's relativity, and that is what facilitates the data analysis. So let's look into the signals that you expect from gravitational. What are the parameters that describe the signal that you can expect from a binary black hole signal? So this is a picture about a binary that is going on a circle. I'm taking a projection, that's why it looks like an ellipse. But if you think about two black holes orbiting on a circular orbit, each black holes, we know that is completely characterized by mass and spin. So you have M1 and M2 are the two masses, and chi1 and chi2 are some way of defining the spin of the black hole, and they are defined in such a way that they are dimensionless, which is much simpler to deal with in a theoretical calculation. So M1, M2 represents the mass of the black holes, and chi1, chi2 denotes the spin parameter of the black hole, which is I just given you how you make it dimensionless. So it's a spin parameter, how rapidly it spins, and this is the spin is made dimensionless in such a way that the spin magnitude can go from 0 to 1. It's a normalization that we have chosen, and black hole in general, GR cannot exceed the spin magnitude of 1. That also helps. So now the only freedom left for the spin is that it can be up or down, and up or down has to be defined relative to some vector, and the natural vector that we have is the angular momentum vector of the orbit. So the L vector that is here, the spin can be either aligned or anti-aligned with respect to orbital angular momentum. That can be plus or minus. But in general, the spins can be arbitrarily oriented. It could be at an angle with respect to angular momentum vector, and that is that we don't show it here, but I will come to in the next slide what that can lead to. So the M1 and M2 are the two masses, and chi1 and chi2 are the two spins of the black holes. And then there is distance. So depending upon how far the source is, your amplitude or the strength of the signal will be stronger if it's closer, and so on. So dl is a luminosity distance to the source, which also gets encoded in the amplitude of the gravitational waveform. Then there are four angles. You can see that theta and phi are the angles which characterize the source's location on the sky. So on the celestial sphere, you want to fix the source's location, and so that require two polar angles. And the iota and xi are two angles which will require to fix the orientation of the orbit with respect to you, because the line of sight makes an angle with respect to the orbital angular momentum that is shown as iota here, and the corresponding polar angle is xi. So you need two angles to specify the location in the sky, and two angles to specify the orientation of the orbit in the sky. So these are the general parameters for a quasi-circular binary with the spins which are aligned or anti-aligned with respect to the angular momentum vector. So they are usually characterized to be as intrinsic parameters. Intrinsic parameters are those parameters which directly determine the geometry of the dynamics of the system, as opposed to extrinsic parameters, which simply tells you where in the sky the source is. So the distance and inclination and so on is not going to determine how the dynamics evolves, because that's mostly going to be mass and spin. Okay? So they are decomposed into two blocks, the intrinsic and the extrinsic parameters, and that's for convenience, which I will not be using much. But I want to tell you that the separation is quite helpful in understanding many of the features and some of the characters which we may take up if there are questions. So you have this is an orbit with spins which are, so we can see that one spin is aligned with respect to the L vector, other one is anti-aligned, which is opposite, but they are either 0 or 180 degrees. Now the orbit can be more complicated. So what is shown here is a binary whose spins are not aligned with respect to the L vector. So L vector, this orbital angular momentum vector, and S1 and S2 are the spin vectors, and S2 is actually almost aligned with respect to the L vector, maybe slight misalignment. But the S1 vector, the first, the primary or the more massive one, is oriented at an angle with respect to the L vector. And what will happen in this case is that since these vectors, these are all dynamical systems, and so there's a total angular momentum vector, that is the J, which is L plus S, and S is actually S1 plus S2. Right? So there's a S vector, L vector, and a J vector, and you will see that like in a precessing top, the S vector and L vector could be precessing around the total angular momentum vector. So as S precesses and as J precesses, it would mean that when the L precesses, L is what defines the orbit. As L precesses, the orbit is going to wobble, and as orbit wobbles, you will expect that the waveform that you expect can have modulations at a periodicity depending proportional to this rate of precision. So what is shown on the bottom, this red curve, is a waveform of a precessing binary, where you can see there are modulations and complicated structures as opposed to the one which we saw for the first detection. Right? So the spin-induced precision can lead to complicated modulations and more structure onto the gravitational waveform, and that is actually good, because when you have more structure, you have more information about the dynamics, though of course you have to estimate more parameters. Right? So that is fine. So that is important to keep in mind, that the processing systems will have more complex waveform structures as shown on the bottom panel. And one more thing to be kept in mind, that when we want to extract the information from the signal, it turns out that our best measured spin parameter are not the component spins, but they are actually a mass-weighted combinations of the spin. So it's like m1 into chi1 dot L. So chi1 dot L is the projection of the spin vector, S1 vector, after some normalization onto the L vector. And chi2 dot L, which will mean that my second spin vector is projected onto the L vector. This combination, m1 chi1 plus m2 chi2 by total mass. So this happens to be the combination that we are able to extract the best from the data. So this is just a theoretical convenience, that what we measure the best from the data is a combination, not chi1 or chi2, and this will turn out to be, I'll show you what role it plays in the actual parameter estimation. So it is something to be kept in mind. In general, what we estimate are m1 chi1 plus m2 chi2 by m1 plus m2, and it also means that if for example the chi1 L and chi2 L are opposite, right, and m1 is m2, in that case, even if the spins are non-zero, just because of the misalignment of the spin, you can get the chi effective to be 0. So that is a strong degeneracy in this parameter, which can actually be vanishing even if the component spins are non-vanishing, just because the way it is projected or the way it is defined. But it turns out that this is what is the best measured parameter. So that is something to be taken in mind, that if the spins are misaligned with respect to orbital angular momentum, that leads to precession. Precession leads to complicated structures, and what you measure the best is actually the chi effective, the effective spin parameter, which can be 0 even if the spins are not, component spins are not 0. Okay, now how do we infer the details of a binary black hole signal using observations, right? So as I said, what we do is that we can compute theoretically the expected gravitational waveforms from binary black hole mergers, or the dynamics of the binary black hole mergers, And this theoretical modeling is extremely crucial in using for data analysis. So in the detection, you use it to construct templates because what you are looking for. So the data analysis problem becomes simpler because if you know what you're looking for, if you know the patterns that you're looking for, the match filtering is a technique that can be used, and that's what we use to detect gravitational wave signals. And what it also helps the parameter estimation, because what we do is that we will have a bank of template, a whole bunch of templates whose properties or the shape we know, and what we want to do is the following. So given the data, we first have a detection, then we take out that chunk of data, and we now know that there's a candidate signal in the data, and we want to ask the question that given the data, what are the parameters of the binary black hole which will fit this data the best? This is something which we do at various scales in our lab. But it's a more complicated problem because of the complicated dynamics and the complicated waveforms that we deal with, and multiple parameters. We have to estimate many parameters at the same time. So basically, this problem of parameter estimation simply is about asking, given the data, we want to ask the question that what are the parameters of the signal that is buried in the data? Of course, data contains noise, and any data analysis you do is subject to the presence of the noise. And noise invariably leads to uncertainties, statistical uncertainties in this measurement. So you do not expect to get a delta function estimates about the masses of spins. There are going to be widths. And suppose if the noise is Gaussian, you would expect Gaussian type probability distributions for various parameters. So you are going to be dealing with probability distributions as the outcome of or answer to this question. And that is exactly this process of inferring the parameters of a signal that is buried in the data using our prior knowledge about the waveforms, using the theoretical models that is available to us, is what is called the parameter estimation. And that it's much more, I'm just oversimplifying it for you, but the way which has to be done is computationally expensive, because you have to ask the question, you have to vary your templates or vary your waveform and find which of them gives you the best fit. And this is a computationally expensive task. And hence, if you want to analyze the signal and so on, it takes days to months, depending upon the nature of the signal and strength of the signal and so on. So, but that is basically what we are after. We want to, in order to infer the properties of a binary black hole signal, you use your prior knowledge of the waveform and use data analysis techniques to estimate the parameters, and which will be subject to the noise artifacts. But that's what we have to deal with. So just to show you why it is interesting, I'm just showing you the differences in the waveforms as a function of spin. So these are for different spin magnitudes and orientations. This is how the waveforms would look like. I've shown only the inspiral part because for simplicity of showing. And I strongly recommend you to go to the Sounds of Spacetime website. So Sounds of Spacetime is a website which will play you the sounds. You know that the frequency of gravitational waves happens to be the audio band, and you can play the chirp signal sounds. And I strongly recommend you to visit this site. But I'm just taking some pictures. So depending upon the spins, the length of the signal could be different, and the details of the signal. So the way in which a waveform would look like for different values of spin. So at the top is the non-spinning system, that's the red one. And as you go, you will see that there are different spin magnitudes, up and down. Plus and plus would mean that both are aligned, and minus and minus would mean both are anti-aligned, and so on and so forth. So this just shows you that just as a function of spin, the waveform is different, and as a mass, it's even more, and so on. So what we use is that we use these differences in the way waveforms are to extract or to distinguish or to extract the parameters of the signal that is buried in the data. So it's just to give you the kind of diversity of waveforms you will get as you change the spin parameter. Of course, this only spin, you can see that you change masses. You also to change the DL, which will be an overall amplitude distance and so on. So it's actually quite a complicated process, but just to give you an idea that we make use of the differences in the way the waveforms look is used very crucially to extract, to do the inverse problem, that is given the data, how this what is the best fit parameters of the signal. So that's how we perform the data analysis or the parameter estimation using that. Right. So now I come. So I spent half an hour. Let's now go to the spins. So what we have seen so far with LIGO, and what have you understood about the binary black hole? So what has LIGO inferred so far about binary black holes? So this is just to give you a quick overview of the 3 observing runs of advanced LIGO. So initial LIGO was like a first phase of it; it didn't detect anything. Advanced LIGO had 3 observing runs: O1, O2, and O3. Is these 3 observing runs? O3 is subdivided into 2 of them: O3A and O3B, which were 2 things separate by a like 1 month gap between them. So the first observing run was is the one where we got this Nobel-winning 150914, the binary black hole merger, and it actually had 3 binary black hole mergers during O1. Then O2 had a slightly more sensitive detector, and it ran for now to 2016 November to August 2017. It recorded 8 signals, of which 7 are binary black holes and 1 was a binary neutron star. So the binary neutron star is a long story in itself. I will not be going into it. But O3 recorded 8 events, of which 7 are binary black holes. Right. And now comes O3. O3 came up after more enhancement in the sensitivity, and you can see that as O3 started, there's a sharp increase in the number of events that we detect. So we are detected. So of course, O3A analysis is still going on. O3B is the second phase of it, which is both O3A, O3B analysis are going on. Now the number of events which are candidate events are quite high. You can see that it's they are much more than that of from the first 2 observing runs, and only 1 event. So there is 1 binary neutron star that was announced, and 1 binary black hole, of which you heard in Anand's talk last week. Are the 2 which are announced, and the analysis is going on. So you can see that with improved sensitivity, there have been an increase in the total number of, I think O3A recorded 33 and O3B 23. And O3B was stopped on March 27 after a bit early because of the COVID thing got onto the experiment. We were not able to run it and so on. So you can see that there's a dramatic increase in the number of events as you go from O1, O2 to O3. And this indeed is going to yield very interesting results. And from the O3 LIGO results are awaited in the next few months. And that will be very interesting. Okay, so just to give you a thing, so you had there's a sharp increase in the number of events as you go from O1, O2 to O3. That's what I want to take from here. Okay. So this shows you, and I'll be talking only about O1 and O2 mostly because that's what is being public. So these are the events that are announced on the O1 and O2 data of LIGO, and these are the time frequency maps which are shown, and the signal is shown in this line. In this as a sinusoid, and so you can ignore here. This is a binary neutron star, it's a long in spiral. You can read. So you can see that the signals come with different types of signals, quite diverse, and so on. So that is shows the diversity that we had already in the O1 and O2 observing runs. So let's examine what are the parameters of interest for us. Right? So let's look into 150914. So we know that 150914, the first detection, had a primary black hole. The massive one was of the order of 36 solar mass. Secondary black hole was of the order of 29 solar masses. So that you would have expected it to give a 65 solar mass black hole, but around 3 solar mass was radiated away in gravitational waves. So the resultant black hole, the newly formed remnant black hole, had a mass of the order of 62, and the spin of the final black hole was around 0.67 in this dimensionless unidimension. Now, as I told you, I'm not showing you the component spin constraints simply because they are very badly constrained. So I'll come to the constraint in a moment of the whole population. Then we also know from the amplitude and using the LIGO, 2 LIGO detectors, that the distance was around 410 megaparsec. That's where we expect typical sources to be. And if you want in terms of redshift, it's around 0.1, 0.09. That's typically you're interested in the masses and spins of the black hole as you keep seeing more, because that's what determines the dynamics of the system as a whole. Okay, so this is the answer to my talk title. This is a picture which shows the component masses of the population that we have seen, the 10 sources that I talked about. And you can see that there are some of them are, as I told you, there won't be a point. You would expect them to be points ideally on the M1 plane, but due to the measurement accuracies, due to the noise presence and so on, there are going to be some kind of contours. And this line is what shows the equal mass. I think M1 is going to M2 line. And this one, at the bottom, you have the binary neutron star, which you can ignore. I will not be talking about it. This is what is the most accurately estimated masses. But you can see that the different sources, which are named after 17, 15, 12, 26, and so on and so forth, which the year, month, and date is how we label them. So this shows you the masses in the component mass plane in this plot. And you can see that mostly, of course, some of the accuracy of the measurements are not good, so they are compatible with a nearly equal mass system. So this is a Q is equal to 2 curve. This one, which doesn't agree with many of them, and so on. And Q is equal to 3 is even outside. So what we have seen in the O1, O2 are mostly nearly equal mass systems, as we can see from the system, from this plot. And on the right hand side is the two-dimensional contours of the final mass and final spin of the black hole that were formed. And you can see that depending upon the mass of the components, the final black hole mass will also range in the entire range. And final spin can also change, though we find that the final spin is not that different, because the final spin will be a function of the initial masses and spins, and we know according to GR how they go, and that's how we infer them. So there is not too much of spread in the final spin, though final mass, of course, spreads across as much as a few from 20 all the way up to 95 also. So this is what we have seen. This is how the whole population looks like. And the important thing to keep in mind is that we were seeing nearly equal mass systems in the O1 ranks. And this is this from the paper that the LIGO-Virgo collaboration wrote, and I strongly encourage you to read the paper, whose reference I have given at the bottom. So now, how about the spin? So I told you that spin, what we measure are the spin parameter, effective spin parameter, and they are mostly consistent with the law spin, except for 1 or 2, which are slightly offset. But that again is giving you indication that most of them are consistent with the law spin. So we do not know why all the black holes that we are seeing are having spins whose effective spin is, for most cases, are enclosing 0. But again, then we know that effective spin 0 may not mean anything. But then it's a complicated thing. So we cannot, with our sensitivity that we have right now, we do not have very accurate constraints on the component spin. So we have to wait for seeing more systems and more improvement in the sensitivity and so on, where we can study the spins of the black hole more accurately, and hopefully O3 should shed more light on the spins of the black hole, though we don't. We have to wait for more. So basically, we are seeing nearly equal mass systems with spins which are compatible with 0. No, 0 or low spin, except for a few. They are almost 0 also. So that's about the spins. Now, if you look into how they compare with the electromagnetic black holes that we know of from the X-ray binaries, for instance, so this blue is what is showing you the LIGO black hole. This is showing you 2 black holes of this one merged to form a new black hole here, and so on. So you can see that, and this violet or this color is what is showing the electromagnetic black holes. Right? So most of the LIGO black holes are of mass higher than 20 solar masses, and that is where the X-ray binary total mass is around 20 solar mass. So we are seeing the LIGO black holes are more massive than the electromagnetic black holes that we know from our galaxy. X-ray binaries is what I mean. And and of course, I'm showing you also in neutron stars, there is a black hole. Yeah, I will not go into the lower mass gap issue here, but I want to point out that the LIGO black hole seems to be it is quite different in terms of the mass of black holes from the electromagnetic ones we have seen from X-ray binaries. Okay, so to summarize, so what are the properties of the black holes? It's nearly equal mass binary. So there's one thing to be kept in mind, that if you have an asymmetric system, the gravitational waves, suppose you fix the distance, a symmetric system, symmetric meaning nearly equal mass binary black hole, would give you stronger gravitational wave emission compared to asymmetric one. So it can also be that there's observational bias due to our limited sensitivity, that we are not able to see these asymmetric binaries up to large distances. Okay? So that is something which will be answered by O3, which has more sensitivity. We will be curious to know if we are seeing more of the asymmetric systems. Then again, as I told you, we are finding binaries which are consistent with rather low spins. And there is no evidence for eccentricity. So eccentricity, I did not talk about. So I talked about binaries in circular orbits, but in principle, two black holes can orbit on eccentric orbits, except that it can be shown that emission of gravitational waves would immediately circularize the binary. So by the time they reach and merge in the LIGO band, you would expect normally that things are all circular. But the only way it will not be circular is if there is some mechanism which is preventing them. So it could be due to a presence of a third object which could be perturbing this evolution, or it could be that it can be many things. I don't want to go into the whole thing. So if you detect an eccentricity, it can tell you about the black hole formation, how the black hole was formed. But at least we are not seeing any evidence for eccentricity from the first two observing runs. So if you look into total mass, it spreads between 19 to 85 solar masses, and component masses are between 8 to 50. That's what the black holes we are seeing in terms of mass. So because we are seeing many of them, we also have some estimate about the merger rate. That means that if you take 1 gigaparsec volume, and what is the rate of mergers in a year in this gigaparsec, and average the rate of merger is about 110 to 3840 in 1 megaparsec cube per year. And there's of course a lot of uncertainty. You can see a factor of 10 or more. And this, as we detect more of them, we will hope to narrow them down. And this is also an interesting thing that how many binary black holes are there, and how frequently they merge, and so on. So the merger rate is going to be is expected to be narrowed down as we detect more and more signals. And these of extreme importance for astrophysics. So this is something which we are looking forward to from O3 and beyond as we get more and more signals. So this is something which Arun talked about. This is this extremely interesting event from O3. This is the only binary black hole so far announced from O3. It's called 190412, and this unequal mass with a mass ratio of the order of 3. And Anand Sengupta in the last week talked about the detection of higher order modes from the system. And I strongly recommend you to listen to the lecture. It's much more, he also talks about the analogy with music and so on. Also, the component spins are, at least the massive component, we are sure that they are not zero. It can be anywhere between 0.2 to 0.6 roughly, that's in the dimensionless units. And it also showed a weak evidence for precession. So precession, as you know, is the phenomenon where if the spins are misaligned with respect to orbital angular momentum, you expect spin vector to be precessing around the orbital angular momentum vector. And there was a weak evidence. You can see that this is a signal-to-noise ratio. It's a way of characterizing a physical effect. You can see that this blue curve is, so this is how you would expect from the noise, in the absence of the noise only. And it's a weak evidence for precession, which is a blue curve. And there's a reasonably strong evidence for the higher modes, which is 3 sigma evidence for the higher modes. That's what is reported. But there is weak evidence for the precession, which is consistent with the companion spin being non-zero. You expect that to happen. Of course, that would mean that as we go to the more and more of the O3, we do hope to see more of this phenomenon, more of these effects, and end up with more stringent constraints, hopefully, on the component spins, which actually plays a very important role on our understanding the astrophysics of these systems. So that's about this. Right. So as we go, we are hoping to see much more interesting sources in terms of the physical phenomenon it exhibits, either higher modes, precision, eccentricity, and so on. And this is, we should be seeing many of these things in the coming years, if not this year, with O4 and beyond. When we are more sensitive, we'll be sensitive to all these diverse types of binary black holes and learn more about about various astrophysical information that were not available to other channels. So in principle, what are we hoping to, what are the kind of open questions that we hope to solve in the coming years? So one open question is, of course, that how are these binary black holes formed? So we are seeing them merging, but we do not know how they were formed. So there are two strong contenders for the formation. One is called the isolated binary evolution. These are systems where you start off with a binary star system with two massive stars, massive enough to end up as a black hole. Then they undergo stellar evolution, and you form a binary black hole. And then this binary black hole merges, as we saw, and that will end up in the LIGO band. So that is what is called isolated binary evolution, which means you're looking into isolated stellar binary evolution. The other contender to that is where you have black holes in dense environment. So there could be in a dense star cluster where there are a lot of black holes, and two black holes could form a binary due to the could end up as a binary due to the interaction. It could be a two-body interaction, like a capture. It could be a interaction involving three black holes, of which one may be kicked out after some time, and so on. So I think there are very rich physics associated with dynamical formation that is available, and we are hoping to know that what fraction of the sources belong to one channel versus other. So these are interesting things which would enrich our understanding of this phenomenon. You can already see that about the 1904-12, which was like an extraordinary event. As I told you, there are many papers already explaining it from various astrophysical formation channels. Right. The second interesting question that we are interested in is about the cosmological evolution of this binary black holes in time. So in the time as a function of redshift. So here I'm saying that if you look backward in time, that is to higher redshift, the merger rate may evolve as a function of redshift, and there is this evolution has to closely do with how the star formation rate, that is the rate at which stars form at this redshift, will be determining strongly how this merger rate evolves. So by probing how the binary black hole mergers rate evolves as a function of redshift, we may get very crucial handle on the stellar evolution or star formation as a function of redshift. It's another thing which we look forward to with more events as we take more events. As yet another interesting thing, which is not about black holes themselves, are about how we can use these black holes to see the universe itself. Right? So as we detect black holes up to very large redshifts, we should be getting information about the cosmic expansion at those redshifts, and we will be, in principle, hope to expect to estimate Hubble constant and various cosmological parameters by seeing these binary black hole mergers. So how we can do this is actually taught by itself, and I hope in future with somebody will be talking about that. But this interesting possibility, which we will be able to do as we detect more and more of the systems in the years to come. So these are some selected questions that I thought are interesting to look forward to in the future, because that's we should know what are the kind of questions we are trying to solve, the big questions. So now, just looking forward, in the next 5 years or so, we are hoping to improve the network of detectors by where in addition to LIGOs and the Virgo detectors, LIGOs in the US and Virgo in the Europe, we definitely hope that LIGO-India can join, and Japan's detector Kagra can also join. So we are hoping to see a world or global network of detectors, which should improve our detectability of the systems, improve the sky coverage, improve the duty cycles, and so on. So this network of detectors can play a very important role in answering all these questions which I just mentioned below. This will be called a 2G global network in the sense of second generation ground-based detectors. And as we go to the next decade, 2030 plus, we are looking to the third generation detectors. I'm just showing you an example. Is Einstein telescope, which is supposed to be a European. This is going to be a European mission, likely underground, so that you can beat the seismic noise. And this is a triangular shaped one. And there is a similar study going on in the US, which is called Cosmic Explorer. And these are much more sensitive than factor of 10 sensitivity compared to the LIGO detectors. And also they will be able to go to very low frequencies, up to 1 hertz or something. So they will be, so as you go to low frequencies, you hope to see more and more massive systems. So they will be, they have very interesting science to offer in terms of the binary black hole mass spectrum that we can probe. So these are two things on the ground, and even more interestingly, on the space, we are going to have LISA detector by 2032 or so. This right now is a European Space Agency mission. It's called Laser Interferometric Space Antenna. It's a triangular spacecraft with about 2.5 million kilometer arm length, which will be orbiting Sun and is going to observe in the millihertz regime, not in the hertz or 10 hertz or 100 hertz. It's going to be observing the millihertz regime, where LISA hope to see the mergers of supermassive black holes. So I told you that the supermassive black holes are believed to be existing at the centers of the galaxies, and the mergers of them, which may be typically mergers of galaxies also, will be tracked by the LISA detector. So we are hoping to get more clues about the supermassive black holes as this LISA starts observing in the next decade or so. So this is going to be, completely complementary, because as ground-based detectors probe the hertz from 1 hertz to 1 kilohertz, LISA is going to probe a totally complementary frequency regime, observing totally different kind of sources, which should enrich our understanding about that should help us understand our probe of the mass spectrum, starting from the supermassive all the way up to the stellar mass. So this is what we are actually looking forward to, and this is a place where I think I should stop and take any questions that you have already posted there. Thank you so much, and I will try to answer the question that will be there. So thank you for your attention. Yeah, so I think the first question as I'm going over is about why does even every galaxy have a supermassive black hole at its center, and how is it formed there? So this is still an open question, as we would need more observation. So the formation of supermassive black holes, the one way of explaining them is by starting from small black holes. It could be building more and more. So stellar mass, it could be going to intermediate mass black holes, and so on and so forth. So it could be a seeding mechanism that could have led to the formation of these galaxies at the supermassive black holes at the galaxy centers. But again, you need to probe them using gravitational waves to understand exactly how they are formed, and verify whether the theories that talk about this evolution are indeed holding true. So we have to wait for one of these things to see. Secondly, what are the primordial black holes, and which class do they belong to? Stellar mass, intermediate, or supermassive? Yeah, so the primordial black holes are the black holes which are formed in the early universe due to the processes which happen soon after the Big Bang, and it can, in principle, span the entire mass spectrum. Though things such as Hawking evaporation have shown that very subsolar mass, in very small mass black holes are unlikely to be stable, so that is ruled out. But even then, if you look into the literature, you can talk about stellar mass black holes which are formed primordially, and people are trying to interpret these black holes in the context of LIGO observation. For example, the high mass of the LIGO detectors were were argued to be consistent with even of a primordial origin. So that's also possible. So it can span the entire spectrum, as I understand. But we have to have very specific features or details of this, of how they evolve, in order to rule out or rule in how these systems, when the mass spectrum of them. Can you tell how the black hole properties, just charge, mass, spin, is determined? Why is it the charge cannot be sustained for long in black holes? Yeah, so I think the charge cannot be sustained for long because it will be neutralized. It's in plasma, and even if it is charged, the lifetime of that charge will be extremely small. So by the time the black hole is stable and so on, you expect the charge to disappear. Now, how they're determined? Right? So as I told you, the mass of the black hole will play a role in the amplitude of the waveform and the phase evolution. As I told you that showed you different waveforms which correspond to different spins, and so the mass and spin for different combinations of the mass and spin, you expect the waveforms to be different, and hence we ask the inverse question that given the data or the signal buried in the data, what kind of masses and spins are consistent, and that's how we determine. So we simply make use of the mass and spin dependence on the waveforms to infer these masses and spins. What causes the matter falling inside the black hole to emit electromagnetic waves? Yeah, I think this is simply because as they fall into the thing, they could get heated up, and this heating, it's like the temperature is high enough, it could be emitting in X-rays and so on. So this is simply simply due to heating of the matter that just falls into the black hole. I strongly recommend you also to watch the video by Professor Shomak Rai Chaudhary, where he has explained many of these things in detail, but it is simply on the heating. So now the second set of topics: which computer language is used at LIGO for instrumentation and data processing? We use all languages that you can think of. That is reasonable because there are you have to connect various types of you have to interface instruments with data analysis, and data analysis with various types of requirements. So depending upon the context in which they work, they use the entire anything that is suited for the kind of analysis or data taking that they do. So I am not an expert, but I know that they use anything that is suited to their purpose. How can we measure the speed of gravity waves? Yeah, so the speed of gravitational waves is not easy to measure. The only reliable scenario in which we have measured it is in the case of the binary neutron star merger that we saw. So we saw the binary neutron star merger to be accompanied by a gamma ray burst, that is electromagnetic wave. So for the first time, we were seeing electromagnetic waves and the gamma ray burst from the same source, and that could be used to set limits, and the limits are extremely stringent. The difference, the fractional difference between speed of gravitational waves and speed of light is of the order of 10 raised to minus 15 or minus 14, 15. That is the kind of accuracy. So that is the way to estimate the speed of gravity waves. That requires something to accompany the thing. And of course, there are indirect ways of using the black hole thing also. That is by using the difference in the arrival times at different detectors, but they are more complicated and has yielded less constraints. I don't want to go into that. So the reliable way of measuring the speed of gravity wave is to by using joint observations of gravitational wave and electromagnetic waves, and see what and constrain the speed of, if the speed of light is same as speed of gravitational wave, which is the case for GR. So GR predicts that the speed of gravitational waves would travel at the same speed as light. We can ask this question whether it is indeed true or not. Why does the advanced LIGO cannot observe binary supermassive black hole? Yeah, so the reason is that the binary supermassive black holes are much more massive. They merge, so you're talking about their merger. They would merge much earlier than they will reach the LIGO band, because LIGO band is from say 30 hertz up to 5 kilohertz or so, and it will merge. So typically 1 million solar mass, the binary black hole would merge in the millihertz regime, and where we have no sensitivity, and that is why we need something in the space to detect them. That is exactly why CLISA is required to see their mergers. do gravitational signals get redshifted? How do we know that signal is redshifted? Yeah, gravitational waves gets redshifted. How we know is not clear, because what happens is that in the gravitational waveform, the m into f is a factor that comes. The mass, the mass times frequency is what comes in the gravitational waveform. So the redshift of the source gets reflected into the mass. So what we actually infer are the so-called redshifted mass, which means that frequency redshift is now transferred to the mass, because that's what we can infer. And in order to lift the redshift degeneracy, so since distance can be independently estimated using gravitational waves, we can use a cosmological model and infer what is. So we have distance, use a cosmological model to see what is that redshift, and then use that redshift to lift this mass degeneracy. And that is how we. So the masses I quoted are indeed all the source frame masses after removing this degeneracy, and this is done by using the distance measurement from gravitational waves and using a cosmological model to get redshift. But we cannot, gravitational waves alone cannot give you directly the redshift at this binary black holes. Yeah, why do gravitational waves diminish proportional to 1 by r? That is how the wave, all the waves go as 1 by r. Right? So that's amplitude decay is same for all. It's not. You're looking at the wave field, and the basics of the wave field will tell you that the wave field will go as 1 by r. The same with electromagnetic field also, except that what we measure there is the flux, not the amplitude. In a binary black hole system, is there a threshold acceleration necessary to start the emission of gravitational waves, and why it intensifies to be present in the LIGO detector? Yeah, there's no threshold to start it, because it will be emitting at a very feeble rate when they are very far away. They'll be emitting, still emitting in principle, but they'll be very, very feeble compared to the sensitivity of LIGO. But only when they emit strong enough and start enter the frequency of these binaries should be in the LIGO band, like 30 hertz, and should be close by, let's say, where the strength of the signal is more, is where we start seeing it. So there is no threshold for onset of emission, but there is threshold for detection that is coming from our limited ability to observe the strength of the gravitational wave. And so that's where it is coming from. Okay, I think sounds like that's all the questions. So now, before I close, I think you should note that there's a talk on 13th May at 4 p.m. to 5 p.m. by Professor B.C. Joshi. The title is Using Celestial Clocks to Discover Gravitational Waves, the Indian Pulsar Timing Array Experiment. So it's going to be interesting talk about a different way of observing gravitational waves, and that's on 30th May from 4 p.m. to 5 p.m. So thank you so much for joining, and join you in the next talk as a viewer. Bye.